Hello, welcome to noise control and its management. Today is the second day of this particular week, and what we plan to do today for starters is discuss a particular example where we will analyze and design a side branch muffler which uses a Helmholtz resonator to reduce the sound in a particular frequency bandwidth. So, here is the problem. So, we will discuss all the details of the example problem. So, what we are told is that let us say there is a pipe and there is sound coming in. So, acoustic power is flowing in and acoustic power is flowing out. The diameter of this pipe dia is 150 millimeters. Diameter of this pipe is 150 millimeters, and what we want to do is we want to develop a side branch muffler for this, and the muffler is such that it has a volume. The volume is 3 into 10 to the power of minus 3 cubic meters. This is given, and then we want to use 3 pipes of identical length and identical internal diameter, 3 pipes. Each pipe is 75 millimeters, 75 millimeters. So, it is 75 into 10 to the power of minus 3 meters each pipe, and the diameter of each pipe is 24 millimeters. So, this is 2A. So, 2A is equal to 24 millimeters, and of course, the length is L. Another thing we are told is that each pipe has a mesh at its entry. So, at its entry I have at the entry port I have put a mesh, and this mesh has a 100. So, mesh size so it is 100 wires per inch. This is given. So, we know that there is an acoustic resistance which is here. Okay. So, the question is that for this type of a muffler we have to find what is the transmission loss, what is the transmission loss at resonance and what is the transmission loss at 70 hertz. So, what we want to know is that if I send in sound at its resonance point of the Helmholtz resonator, how much sound is going to come out, or if I send sound at 70 hertz, how much sound is going to come out. That is what I am interested in finding out. And finally, we are given 2 additional details, that the temperature of air inside the whole system temperature is 325 degrees centigrade. So, some hot air is passing through, pressure is 110 kilopascals. So, for these conditions my density of air is actually pretty low, 0.641 kg per cubic meters, and my speed of sound is high, 490 meters per second. So, we have to use all these data to compute transmission loss at resonance point and transmission loss at 70 hertz. So, we will start doing our math for this. So, the first thing we have to do is we have to find LC, LC. So, LC equals L plus LA plus LB. Now, when we look at this geometry, okay, when we look at this geometry, each pipe has a long flat surface area on both the ends. Of course, there is an opening here. Okay. So, I will draw it more clearly. So, each pipe is like this, and on one end it is connected to the volume, and on the other side it is connected to a pipe, right. So, this pipe and this volume, they act as flanges, So, we will use the relation for flanges. So, what is L? L is 75 millimeters, and LA will be same as LB because both the ends are flanged. So, this will be 2 times 8 times A divided by 3 pi, and all these are in millimeters. So, I have to multiply by 10 to the power of minus 3. So, what I get is 95.37 into 10 to the power of minus 3 meters. Now, I can use this LC to compute acoustic mass. Now, for one pipe, the value of acoustic mass is rho naught LC divided by pi A square for one pipe, but there are 3 pipes. So, I have to multiply it by 3. Okay. So, if I do all the math, I get density is 641 times LC 95.37 into 10 to the power of minus 3 divided by pi into radius of each of these thin pipes is 12 millimeters. So, 12 into 10 to the power of minus 3, whole thing square, okay, and of course, multiplied by 3, and what I get is 405.4 kg per meter 4. So, that is my acoustic mass, and finally, my acoustic compliance is V divided by rho naught C square. V is 3 into 10 to the power of minus 3 cubic meters divided by density 0.641 times speed of sound square 490 square, and that gives me 1.949 into 10 to the power of minus 8 meter to the power of 5 divided by newtons per newtons. Okay. So, we have calculated acoustic mass, acoustic compliance, we also have calculated the effective length. Now, we have to find the transmission loss at resonance and transmission loss at 70 Hertz. So, first we have to figure out what is the resonance point of this system, and in the last class we had defined that the resonance point for a Helmholtz resonator is what? 1 over 2 pi square root of 1 over MACA. So, if I plug in all the values, this thing will resonate at 56.62 Hertz. This is the resonance point. Now, we start doing the calculations. So, now we will do transmission loss at resonance. Okay. Transmission loss at resonance. Now, let us see, in my relation I had said that to compute transmission loss I have to find AT, and to find AT I have to know what is RA and I have to know what is XA. Okay. And XA is 2 pi f times MA minus 1 by 2 pi f over CA. So, we have already calculated MA and CA. So, we can calculate XA, but we still do not know RA. So, let us calculate RA. So, Ra is what? This is the acoustic resistance of all the 3 pipes combined for one pipe, and this pipe has a mesh. So, it is Rs divided by pi a square, and because there are 3 pipes, we divided by 3. So, the mesh is having how many wires per inch? 100 wires. So, we go back to the table and we see that for 100 wires the value of Rs is 9.1. Okay. So, this is 9.1 divided by pi, A is 12 millimeters into 1 by 3. So, if you do all the mathematics, this works out to be 6705 Pascal seconds per cubic meters. Okay. The second thing we have to compute is XA. Now, what is XA? XA is the reactance of the system. Reactance of the system, and this is equal to 2 pi f ma minus 1 over 2 pi f Ca. Now, if you think about mechanics or electrical engineering systems, the reactance of any system at resonance point is 0. So, I can directly write this value as 0. But if you are not convinced that I am writing this correctly or not, what you can do is you plug in the value of f as 56.62 Hertz and also ma the value which we have calculated earlier 405.4 and Ca as 1.949 into 10 to the power of minus 8, and if you do the calculations you will find that this value will be extremely close to 0. You will still have a non-zero value because of calculation errors, because you will not be able to compute till a very large number of decimal places. So, because of decimal place error you will have small value, but it will be very close to 0. So, here I am saying that because of resonance I can directly write Xa as 0. If the frequency of interest was not resonance, if the frequency of interest was not resonance, then I will not be putting this number as 0, then I will have to actually calculate it. So, this is there. And the other parameter we have to calculate is S. So, what is S? S is the cross sectional area of this pipe, and we know that the diameter of this pipe is 150 millimeters. So, S equals pi d square by 4, and if I plug in the value of d as 150 millimeters, my cross sectional area is 0.01767 square meters. So, this term rho naught c divided by 2s becomes 8888. So, my transmission coefficient AT equals Ra square plus Xa square divided by Ra plus rho naught c by 2s square plus Xa square, and if I plug in all these values I get 0.1849. So, my transmission loss at resonance is equal to 10 log of 10 1 over 80, and so this equals 10 log of 10 1 over 0.1849, and if you do the math this comes to be 7.33 decibels. So, this is one part of the answer, but we were told that we have to find what will be the transmission loss at 70 Hertz. what will be the transmission? So, at resonance the transmission loss is 7.3 decibels. At 70 hertz we are trying, now we will calculate the transmission loss. So, this is the second part, TL at 70 hertz. Okay. So, again for transmission loss we will be using this relation. Now, in this relation RA does not change with the frequency, neither does rho naught C divided by 2S change with frequency. However, what does change is XA, because it is dependent on frequency. So, all we will do is we will recompute XA and plug the new value of XA in this equation for AT, and then we will again recompute TL or transmission loss. So, XA at 70 hertz is equal to, so what is this, 2 pi f MA minus 1 over 2 pi f CA, and if I do all the math, this comes to be 61,664. So, AT equals 6705 square plus 61,664 square divided by 8888 plus 6705 whole square plus 61,664 square. Okay. So, this comes out to be 0.951. So, what is AT? It is basically equal to the ratio of W out divided by W in. Okay. So, what this tells me is that at 70 hertz, if I am sending 1 watts of sound energy, 0.95 watts are getting out. So, virtually all the sound is getting out. So, this resonator is not doing a good job at 70 hertz, but it does a pretty good job at resonance, you see, because the value of AT is 0.1849. If I send in 1 watt, only 0.18 watts are getting out. So, and in terms of transmission loss, this is equal to 10 log 1 over 0.951, and that comes to be pretty small, 0.22 decibels, 0.22 decibels. So, what we see is that the resonator acts as a very good, suction. It sucks in sound at resonance, but it does not do a good job in terms of removing that sound if I move away from the resonance. And if I plot, let us say, my frequency, and let us say I plot on the y axis transmission loss, I will get a curve something like this. So, the transmission loss will be very high at resonant frequency, and as I move away from the resonant frequency, the transmission loss will be less, and as I keep on going away from the resonant frequency, transmission loss will become more and more, I mean it will become lesser and lesser. Okay. Ideally, a good, so I can design my Helmholtz resonator in such a way. So, what I want is that if this peak is like this red line is also a possible solution. I can design my resonator, Helmholtz resonator, which resonates at the same frequency, but it has a sharper peak. It has a sharper peak. And what does a sharper peak mean? That even if small amount of sound is coming away from the resonance, it will not get attenuated. So, we want our resonator to have a wider this peak, wider, it should not, the peak should not be very sharp, it should be a little fat peak, it should not be sharp peak. So, this nature is called half power bandwidth, or first we will talk about quality factor. So, there is a parameter called quality factor, okay. And what does it mean? That if the quality factor is large, if the quality factor is large, then peak is not sharp, and if the quality factor is small, then the peak is sharp, okay. So, we want that the quality factor should be large, we want that the quality factor should be large, and the relation for this quality factor is 2 pi f naught, f naught is the resonance frequency times acoustic mass divided by Ra, okay. So, this is one way to quantify how sharp this peak is in terms of quality factor. The other way to quantify how sharp this peak is by a term known as half power bandwidth. Okay. And that is defined as 1 plus quality factor square times 4 divided by, okay, so minus plus 1 divided by 2 q naught into f naught. So, if this half power bandwidth is wide, the peak will be not sharp. If the half power bandwidth is less, then the peak will be very sharp, okay. So, this is another. So, this is actually in the denominator it is QA. Actually, I must correct myself, if the quality factor is large, then the peak will be sharp, and if the quality factor is small, then peak will be not that sharp. So, I misspoke, okay. So, in these two ways we can quantify how sharp this peak is, because we are not only, because in natural systems, in natural situations, we will never have a situation that only sound at one particular frequency will be coming. There will be always sound in the neighborhood of a particular peak frequency. So, we want that whatever, if we want to kill sound of a particular frequency, we want that it should work, the resonator should work not only at that particular frequency, but also around that frequency, and the resonator will not work around the frequency if its peak is going to be very sharp. So, we want that this half power bandwidth should be as large as possible, okay. So, this concludes our discussion for Helmholtz resonators. Starting tomorrow, what we will do is we will discuss another type of side branch muffler, where we are going to use closed tubes. So, remember earlier in the beginning of this class we had said that we can have side branch mufflers of type 2, where I am having a Helmholtz resonator, or I can have a side branch muffler where I can just attach on the side a closed tube or a short open tube. So, we will discuss these two tubes also tomorrow. So, with that we conclude our discussion, and we will meet once again tomorrow. Thank you.